Hemoglobin is an essential protein in the human body. It delivers oxygen to your tissues, returns carbon dioxide to your lungs, and is a primary component of red blood cells. An important thing to note about hemoglobin is that its reaction with oxygen is also an equilibrium process. For the purpose of this investigation, we will only be considering hemoglobin's reaction with oxygen molecules. This is the chemical equation for hemoglobin. Since it's long and arduous to write, we'll be abbreviating it to HB. This still represents the above molecule. This is the equation for hemoglobin's reaction with oxygen. We'll keep this down here, as we'll be using the equation throughout. When hemoglobin reacts with oxygen, it can be split into two defined parts. The first is in the lungs, where oxygen is picked up, and the second is in the rest of the body, where it is diffused in the blood and tissue. Firstly, the red blood cell, which is mostly hemoglobin, goes to the lungs and bonds to 4 additional oxygen molecules, as can be seen here in the equation. A fun fact about hemoglobin is that its bonding with oxygen is cooperative, meaning that once one oxygen molecule is bonded, the hemoglobin's affinity for oxygen increases, and other oxygens bond more easily. Cool. Back to the body. Once the hemoglobin is saturated with oxygen, it will begin to move around your body through your veins and diffuse oxygen into your tissues and blood before returning empty-handed to your lungs. Let's use that equilibrium equation to explain why this happens. When you take a breath, your lungs fill with air and oxygen, raising the concentration of oxygen molecules. This, according to Le Chatelier's principle, puts stress on the equilibrium and causes it to shift right to lower the amount of oxygen, bonding the oxygen molecules to the hemoglobin. Since your body consumes oxygen, its concentration is lower in your blood. This stresses the equilibrium to shift left to increase oxygen consumption, or concentration, unbonding it from the hemoglobin as it diffuses into your tissues. The empty hemoglobin then returns to your lungs, where the process begins again. These stresses can occur outside of breaths as well. In your lungs, an increase in pressure when doing something like scuba diving compresses the air, allowing for a higher concentration of oxygen and shifting the equilibrium even further right. In your blood, when your body is at rest, it consumes less oxygen, making the concentration higher than usual and keeping some hemoglobin oxygenated so as not to waste any oxygen. These stresses are not the only ones to affect this equilibrium. It can also be shifted left by lowering the concentration of oxygen. A raise in altitude, when, for example, mountain climbing, would leave less oxygen in the atmosphere and therefore lower its concentration in the lungs, stressing the equilibrium to leave more oxygen unbonded and therefore lowering the amount of oxygen that makes it to the bloodstream via the hemoglobin. In your blood, the equilibrium would be shifted right when your body is consuming more oxygen, therefore lowering its concentration, for example, when exercising. This would further encourage the hemoglobin to release the oxygen into the tissues, increasing the oxygen supply to the body. What's interesting is that these situations and these stresses occur and actually have more than one stress on the equilibrium to shift that way. Mountain climbers would experience a shift to the left as the equilibrium tries to adjust to the lower oxygen concentration, but it would also shift to the left as a result of the lower pressure, as the equilibrium would want to produce more molecules to increase pressure in the lungs. These combined factors result in less oxygen making it into the bloodstream, which presents the danger of a climber tiring easily, blacking out, or suffering from hypoxia. Scuba divers experience the same issues, but in the opposite direction. The higher pressure allows for a greater oxygen concentration in the lungs, shifting the equilibrium right, but it also stresses the equilibrium to shift right to lower the pressure in the lungs by producing less molecules. These two factors combine to force more oxygen into the bloodstream. Compressed air would also have a higher oxygen concentration, shifting the equilibrium even further right, and the exercise of swimming would cause the body to consume more oxygen, returning more unbound hemoglobin into the lungs with each breath and, again, forcing the equilibrium right. This presents the danger of forcing too much oxygen into the diver's blood, threatening them with oxygen toxicity, which can cause permanent nerve damage. Because of these stresses, both climbers and divers need to consider their breaths. Climbers may take compressed air with them to manage the oxygen concentration, while divers must learn to regulate how often and for how long they dive in a short time. Let's recap. Hemoglobin's reaction with oxygen is in equilibrium. It becomes oxygenated in the oxygen-saturated lungs, then diffuses it into the oxygen-starved body. Each breath in your lungs shifts the equilibrium right, oxygenating more hemoglobin. When it pumps through your blood, the equilibrium is shifted left, and the hemoglobin is encouraged to release the oxygen. These shifts can also be caused by environmental stresses. Mountain climbers experience a shift left, getting less oxygen and threatening to make them black out, while divers feel a shift to the right, getting too much oxygen and threatening them with oxygen toxicity. Understanding this hemoglobin process is so important because it's essential to how we breathe and stay alive. Thank you for watching, and thanks to all these awesome sources for helping me understand this process. Next time you want to try an equilibrium reaction, just take a breath. After all, it's how we live.